There we go. Is the recording on? Okay, good. Well, good morning, everyone. I realize this thing has rather the atmosphere of a boot camp. So every lecture is approximately 1 week of Comp 330 in the regular term. So as we approach the end of the week, it can be getting quite tiring for you to keep pace with, excuse me, with all this material. So I will try to go a bit slower today, mainly because I'm also getting tired. As you can see, I haven't had time to shave, but every Sunday I'll shave. So, so at least on Mondays, you'll see me looking fresh. So I'm going to do the pumping lemma today. And then after the break, I'll get back to Kleene algebras. So I have put up notes on the pumping lemma on the course web page. Two sets of notes. The first one describes the statement of the pumping lemma, and more importantly, its contrapositive. And the second one just does some examples. So for those of you who like examples, there you are. There are some examples, and believe it or not, I'm going to do examples today. And after the break, we'll do some Kleene algebras, and we'll probably end a bit early, but I'll stay on to chat if anybody wants to chat. Just out of curiosity, does anybody feel the need for me to hold office hours? Or are you happy with chatting with me at the end of the class? No answer. Okay. I remind you that our teaching assistant, Michael Woolman, will be holding office hours tomorrow, I think 11 to 1, but I will verify that and post that on the course webpage. Okay, good. So let us begin. So we have already seen that this language, so consider this language L. Which has a block of A's followed by an equal length block of B's. So by the way, this notation, A raised to the power n, means just repeat the symbol A n times. It's an informal notation. It's nothing to do with mathematical exponentiation or arithmetic. It just means repeat A n times. So if I write AB in brackets to the power n, I mean AB, 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 AB repeated n times. So here I mean A is repeated n times, and by using the same superscript on the B, I'm saying B is repeated an exactly equal number of times. And right on the first day, I asked, how does one design a DFA to recognize this language? And very quickly, it was pointed out that this is not possible because there's no way that with finite memory, you can keep track of how many A's there were. And you need to keep track of how many A's there were if you're going to count off and see that there are equal number of B's, right? So that's a very powerful intuition, and it is paradigmatic of the arguments that we use to delimit the power of finite automata. So right off the bat, we see there are some languages that are not regular. The next module, where we study context-free languages and push-down automata, that is basically DFAs equipped with a stack for extra memory. Those things can recognize this, but plain old DFA definitely cannot. So let us argue how this works in slightly more detail. So supposing we have a putative DFA that supposedly recognizes L. Okay, so let's say somebody claims, yeah, this one recognizes L. How will we analyze this claim carefully? So there's some start state. It's supposed to be a DFA, so unique start state. And then we wander through the machine reading a bunch of A's, and we reach some state. And now, if the string is long enough, so let's say it's a finite state machine, so it has some number of states, maybe a big number, but no matter how big it is, I can choose an even much longer string. In particular, I can make my string so long that the block of A's is by itself way longer than the number of states in the machine. So if that's happening, then at some point, I'm going to have to hit a state twice, right? While I'm still reading A's. So that means I have a situation like this. Ah, what happened? So I have a situation like this where as I'm reading the A's, I hit some state, and then as I wander through the machine, I reach that same state again. And then maybe I'm still reading some A's, and then I reach some state, and then I start reading B's, and finally I reach an accept state. And supposedly, this string has been accepted because it has an equal number of A's and B's. But if I look at this loop, and I'll say, well, if I could go around that loop once and end up back here and read the rest of this string and get to an accept state, why can't I go around the loop twice? So that means I now have more A's, but the same number of B's, and so they can't possibly be equal anymore. So this string, this machine can't possibly be accepting only strings with an equal number of A's and B's. Okay, so is this argument clear? It rests on a very, very fundamental principle in mathematics called the pigeonhole principle. This principle was named by the Brits. That's why they called it the pigeonhole principle. I guess in America, it would have been called the mailbox principle. The idea is if you have an array with, let's say, n boxes, and you try to stick m things in those n boxes, and m is bigger than n, one of the boxes must get more than one element. So similarly here, if you have more A's than there are states, at some point, you have to hit the same state twice as you process the A's. And because of that, we have a configuration like this. So this wavy line represents wandering through the machine from state to state. And because we have this loop, you can say, well, if I've reached that loop, I can just go through the loop like 17 times if I want, be back here and then read the rest of the string. So I'm getting all these extra A's and still the machine is forced to recognize it. So that's why this is called the pumping lemma, because it says, once you have a loop like this, you can treat it like a pump. You can just keep on putting in loops of A's and it'll always have to be accepted. Okay. You can also say, hey, I've reached here and then I have this loop that brings me back. Why should I bother to do the loop? I'm just going to skip it and keep going. So that also means you can pump down by removing some A's. You still have to have a string that's accepted. In either case, it shows that A to the n, B to the n cannot be accepted by this machine exactly. Okay, so I want to write the formal statement of the pumping lemma. I'm not going to write down a formal proof because I think this picture indicates how the formal proof would look. But so here is the formal statement of the pumping lemma. Let L be a regular language. So I warn you right off the bat, this statement is going to have several quantifiers. So it will require some subtlety and some concentration to understand the statement. Let L be a regular language. There exists a natural number P strictly greater than 0, such that for every word in sigma star, if W is in L and length of W is greater than or equal to P, there exists XYZ. So 3 strings in sigma star such that W equals XYZ concatenated. So basically it says, I can take my word W and break it into 3 consecutive pieces, X, Y, and Z, with the conditions length of XY is less than or equal to P, length of the Y portion is strictly positive, okay, and for all I in the natural numbers, X, Y to the power I, Z is in L. Okay, so note all these quantifiers. Okay, so here's one, here's another, here's another, and here's another. So 4 quantifiers, and how many alternations? 1, 2, 3 alternations of quantifiers. Okay, so this is quite a non-trivial statement to analyze. Oops. So proof idea. Is basically the picture I've already shown you for A to the N, B to the N. So part of the assumption is that it's a regular language, which means it's recognized by a deterministic finite automaton. Since it's a deterministic finite automaton, we know that if we choose a string large enough, so given a DFA for L, choose P to be strictly greater than the number of states in the automaton. All right. And after that, we know that if we choose a word whose length is strictly greater than p, if the length of W is strictly greater than or equal to P, and W is in L, then as the automaton moves, or as the automaton changes state, it must hit the same state twice while reading the first P letters. W. And so we get a picture like this. You're in your start state, you reach some state, you reach that a second time, and then you go on and you hit some accept state. Somebody might say, why is there exactly one place where you loop? Of course there's not. You might have a dozen places where you're looping, but I'm just paying attention to one of them. Any one will do. I just know there has to be at least one. So we'll call this the portion of the string that gets you to that first repeated state the first time. We'll call that X. We'll call the piece that brings you back to that state Y. We know that this already happens before P because P is greater than the number of states in the machine. We know that the length of Y is strictly positive. It can't be zero because we otherwise wouldn't count as hitting the same state twice. And whatever's left, we'll call Z. And now we look at this path through the machine and we note, well, if this path leads you to an accepting state, well, once I reach Y, I can go around as many times as I want, including 0 times. And it has to then get me to an accept state because it's a deterministic machine. Once I'm here and I'm reading Z, I have no choice. It's not like I can make choices and go to different places. So if Z used to get me from here to an accept state, it has to always do that, no matter how I got there. Okay, so that's basically the proof of the pumping lemma. So so we will say that a language can be pumped if it has this property. There is a P such that for every word of length greater than P, you can find a word, you can find a way of breaking up that word so that the middle part is of non-zero length, and that can be iterated. Now you might have some doubts about this statement. So first, recall, I don't know if I should say recall because I'm not sure I ever told you this. Every finite language is regular. This is just a fact. Every finite language is regular. How do we know? Well, easiest way is to note, I can take every single word in the language, there are only finitely many, and write down exactly that word as my regular expression, and plus the next word, plus the next word, and it's finitely many pluses, so it's in fact a regular expression. So there must be an automaton for it. So any finite language, straight off the bat, is regular. Well, if it's regular, how the hell can I pump it? I mean, sorry, if it's finite, how the hell can I pump it? Well, so the point is, in that case, the P that you choose is bigger than the length of the longest string in the language. And now you see this universal quantifier. For every W of length greater than or equal to p, well, there aren't any such strings. So it's vacuously true, everything you say thereafter. It still satisfies the pumping lemma. It's just that there are no strings of length greater than p. But of course, if your language is indeed infinite, there's going to be no longest string, and you will find pumpable strings. Now, so that ends that remark about finite languages. It might have raised some doubts in your mind about the truth of the pumping lemma, but I hope I've dispelled them. So let us see what this lemma actually says. L regular, sorry, that is not very nicely written. L regular implies L can be pumped. It does not say L can be pumped. Implies L regular. In fact, on assignment 2, I'm going to give you an example of a non-regular language that you can pump. But anyway, so please note this fact. So pumpability is not a way of proving that a language is regular. It's simply false that L can be pumped implies L regular. We have counterexamples to this. So what is the use of this lemma? Let us look at the contrapositive version. L cannot be pumped implies L not regular. So this is, of course, just the contrapositive of the statement of the pumping lemma. But this is the form that we will use. We use the pumping lemma to show that languages are not regular. And how do we do it? We'll say, aha, I'm going to take this language and convince you that it's not regular by showing you that it fails pumping. Okay? And basically the rest of this session is examples of this, of proving languages are not regular. Now, let's write down the contrapositive form explicitly. So we'll say, suppose L is a language in sigma star, a subset of sigma star. I'm not saying anything about regularity now. L is any old language such that, so how do we negate a statement with lots of quantifiers? You put the negation outside and then you push it in, and the way you push it in is every quantifier flips. And then you bring it all the way in, flipping quantifiers as you go. And then of course, now you've got a purely propositional formula and you just negate it using the usual Boolean algebra rules of what negation means. So we're going to do that. So such that for all, you see that existential has become a for all. For all p greater than 0, there exists W in L with length of W greater than or equal to P, such that for all X, Y, Z in sigma star with W equals X, Y, Z, length of X, Y less than or equal to P, and length of Y strictly positive, there exists I in n such that x y to the power I, so y iterated I times, z is not in L. So supposing all this implies L is not regular. Okay. So I think you'll agree with me, a statement like this has lots and lots of quantifiers, and it becomes a pain to deconstruct it. There's one, there's one, there's one, and there's one. How do we understand a statement with this level of logical complexity? And by logical complexity, I'm referring to the number of times the quantifier flips, because it's the flipping of the quantifier, not just the number of quantifiers, that is really significant. Now, so our strategy to try and understand these kinds of statements is through use games. To deconstruct the statement. Okay, so we're going to always be given a language and we're going to try and prove all this. And if we succeed in proving all this, then we know L is not regular. So what does it mean to prove all this? So it's a two-player game. Played between you. So we will depict you like this. You have a little halo because you're an angel. And the devil. The devil is always holding, for some reason, the Greek letter psi and has horns. Okay, so you play the existentially quantified variables. The demon plays the universally quantified variables. You must excuse me. Hello? Yes? Oh, hi, Jan. I'm in the middle of a class that I'm teaching by Zoom. Yes, so I finish at 1. Is that a good time? Do I have your number? Let me make sure. I have, yeah. Yeah. 3355. Okay, very good. Great, thanks. So you must come up with a winning strategy. So it's not sufficient to say, well, if the demon makes a stupid move, I will take advantage of it and win. You have to have a winning strategy. So what is a strategy exactly? It's a thing that says, I have a response for any move. You can see why the demon is playing universal quantifiers, because you have to be ready for anything. So you can see that the notion of universal quantifier is built into the notion of your enemy, right? Because your enemy is trying to choose anything it can to try and screw you over, right? And you have to be ready for it. That's the only sense in which you can have a winning strategy. So the demon's moves let me say the demon's first move is just represented by a symbolic P. You can't say, well, let's assume P is 10. You have no idea what P is. The demon is choosing P, not you. So you can't say stuff like that. So you just have to say the demon chooses some number P, and you have to deal with whatever P might be. So the only way you can deal with all these infinitely many choices that the demon might make is to say P is some unspecified number and I'm going to respond anyway. Okay, so the demon makes, so then step 2 is your move. You get to pick a word. You'll use the symbolic value of P in how you construct that word, but it is your move. You get to actually explicitly choose a move. So your first move is explicit. You see, the third move is the third quantifier, and it's a universal. So it's the demon's choice. You don't get to say, oh, well, if this was the XYZ, I'm home free. No, you don't get to choose the XYZ. The demon gets to choose it. But of course, the demon is constrained by the fact that you have chosen you have chosen W. So the demon has these constraints. He has to choose W to be equal to the concatenation of X, Y, Z. Can't just choose X, Y, Z arbitrarily. The demon is constrained to make the length of XY less than or equal to P, and the demon is constrained to make Y strictly positive, the length of Y strictly positive. Okay, but apart from that, the demon has complete freedom. You don't get to say, let's pretend X is this and Y is this and Z is that. So the demon's move in step 3 has to be analyzed by an exhaustive case analysis. And this is the part that people find the most challenging, to look at all possible things that the demon might do. Right, so you have to say, well, the demon could do this, the demon could do that, the demon could do that. You have to make sure that you've covered all possibilities, and you must make sure you have a response for all possibilities. And finally, your last move must specify a response for all cases. Okay. So let's do a super simple example, one that we are totally convinced already is not regular, but we'll play the game with the demon just to see the format of how you should write up these proofs. So the language is the familiar one. So step one, Demon chooses P strictly positive. And then you use that P in your first move. You choose W equals A to the P, B to the P. So remember, you get to choose any word longer than P. Some people think that they have to choose W to be of exactly length P. Nobody said that. So you see this one is twice as long as P. Now, the demon is constrained by length of xy is less than or equal to P to choose y to consist exclusively of A's. Yes, because I chose my word so that the block of A's is already of length P. So since xy has to fit into the first P, that y part, of course, has to fit into the first P. Y can only consist of A's, and y cannot be of zero length. So y equals A to the K for some K strictly greater than 0. So K is greater than or equal to 1. And Demon has no other choice. So then I choose I equals 2. So you see the explicit nature of your choices. You've chosen an explicit word. You've chosen an explicit number. Of course, in more complicated examples, that explicit number might have several cases, and it might be a formula based on other things. And so now the word x, y to the I, z, well, x, y to the I is x, y, y, z. We know that we know that the extra y has added k more a's. So this is a to the p plus k, b to the p. And this is not in the language. Thus, L is not regular. So this is a simple enough example, but I want to be sure that everybody groks the logic, because we're going to now do more tricky examples. So let me pause. Anyone with doubts about the logical pattern that we're following? Adam, anyone saying anything on the chat?
No, nobody is saying anything in the chat.
Okay, let us go on. So this covers the first set of notes. So let's do a number of examples that are based on both the one-letter alphabet and the two-letter alphabet. Cool. So here's the first one. So we're going to pick, so this is from now to the break, just all examples. Example 2. So a language is going to be with the one letter alphabet, a to the q, q a prime number. So your intuition should be screaming at you. Of course, this is not regular. A finite automaton can't even count. How is it going to check for primality? But we still need a formal proof, right? So what I just said is an intuition, certainly not a proof. So we're going to play the demon game. So demon picks P. So then I, with my halo glowing in full form, pick a to the n, where not when, where n is strictly greater than p and n is a prime. Yes, so I hope everybody knows that there are infinitely many prime numbers. So no matter what number the demon picks, there's a prime number bigger than that. All right, great. So now what does the demon do? Demon has to pick y equals a to the k, where k is strictly greater than 0. Well, there's no other letter than a, so whatever the demon picks, it's going to be a to the something. But let's look at the constraints on this k. It's got to be less than or equal to p. Remember, we said that y has to be of non-zero length, but x, for all I know, is of 0 length. There's no constraint like that on x. It's that the total length xy has to be less than p. So it could be that the whole of xy is actually just pure y. So the only constraint I know is that k is less than or equal to p and it's strictly positive, can't be 0. So then I pick I greater than 1. Exact choice is deferred until we do some analysis. And now, of course, if I was really writing this out, I would just say, and by sheer genius, I chose I to be this, and we'll see the calculation works out. But now I'm imagining that I'm trying to work this out for the first time. So I'm saying, okay, I'm going to pick some I. Let's see what it implies. So it implies the new string is a to the n plus I minus 1. Why I minus 1? Because one of the copies of y, of course, was already in the original string. So the new string is that. Okay. And now I look at that and say, how can I make sure that this thing is not a prime number by choosing I appropriately? So now I say, aha, choose I equals n plus 1. Then the new string is a to the n plus nk, which is a to the n plus 1 times k, and n plus 1 times k is sure as hell not a prime. So L is not regular. So when you're doing these, maybe you'll have to do some scratch work and fiddle around until you come up with the right thing, the right choice for I. In some examples, it's like trivial. In other examples, it's not. And some of these things, by the way, are not at all easy. So by the way, there is another pumping lemma I will teach you in a week or two, maybe 2 weeks. And that's the pumping lemma for context-free languages. And that's much harder to use. This one is usually not very difficult to do. So let's try another example. Let's see, that was example 2. Let's do example 3. So here the language is a to the n, b to the m, with n not equal to m. So this is very similar to the language a to the n, b to the n. Somehow it's the opposite constraint. I want to insist that they're not equal. But to check that two things are not equal also involves counting. I have to count and see that they're not equal. So you should expect this is not possible. And now you can try to do this with the pumping lemma. And it's possible, but basically hard to do directly with the pumping lemma. Yeah, hard to do directly with the pumping lemma. Which doesn't mean impossible. I'm sure you could do it, but it is not completely straightforward, and there is fortunately an easier way. So I'm now going to show you other techniques other than just doing it blindly from the statement of the pumping lemma. So Adam, what's the chat about?
The chat is just saying that on example 2, it should be n distributed to 1 plus k rather than k distributed to n plus 1.
What did I write?
You wrote n plus 1 times k. The chat thinks it should be...
So let's see, that's n plus 1 minus 1, so that's nk. It's n times k plus 1, yes.
Yes, that's what the chat is saying.
Ah. Thank you. So I guess this.
You only changed one of them.
Yes. Okay, thanks. Right, moving right along. So hard to do this directly with the pumping lemma. What can we do instead? So we can look at L complement. So here is where you use what we discussed about closure properties of regular languages. If L is regular, then L star is regular. If L1 and L2 are regular, then L1 concatenated with L2 is regular. If L is regular and if L1 is regular and L2 is regular, then L1 intersection L2 is regular. If L is regular, then L complement is also regular, right? We proved all these things: union, intersection, complement, concatenation, and Kleene star all preserve regularity. So if I'm looking at a language and I say, can't tell whether this is regular or not, and then I intersect it with a language that I know for sure is regular, and then I look at the result and I say, wow, this is absolutely not regular, well, then the first language cannot have been regular either, right? And that is the strategy to employ. Now, what is L complement in this case?
I think L complement would just be like example 1, a to the n, b to the n.
Wrong. So this is exactly what it's not. So it will include that set, yes, but it could have B's in front of A's. It could have some A's and some B's and some A's and some B's. Anything that doesn't satisfy this condition. So it doesn't have to be, oh, a block of A's followed by a block of B's, and now that the numbers exactly match. Okay, so L complement is actually a big mess. So does everybody understand why? So to violate this description, one way of violating is the way Adam said: you have some A's and some B's and the numbers match, but I can also do completely other things. Have several blocks of A's and B's alternating in all kinds of weird ways, and that'll also not fit this pattern. Because this pattern said one block of A's, one block of B's. So you can't classify all of them. I mean, yes, you probably can, but we have much simpler things we can do. But now if we take L complement and we intersect it with A star, B star, now A star, B star certainly is regular. So L complement intersection A star, B star says, okay, so now I'm choosing only those words that have some number of A's followed by some number of B's, and they have to now violate this condition. So then we get exactly A to the N, B to the N. So this is not regular. So L is not regular. You might look at this and say, but okay, we did this and we never used the pumping lemma. But of course, how do we know this guy is not regular? Well, that was a pumping lemma proof. So the point is, once you have a stock of languages that you know are not regular, and this is certainly one of our favorite ones, you don't always have to do pumping. Sometimes just some Boolean algebra will get you there without having to explicitly do pumping. Sometimes you have to do a bit of Boolean algebra and then do another pumping argument. So you do the Boolean algebra to massage the language into a form for which it is easy to do pumping. So this one, it was so easy that by doing the right kind of Boolean algebra, we got a language that's like in your face, not regular. But not everything is so simple. Okay, let's do another example. So I just want to make sure everybody understood this point, why L complement is not just A to the N, B to the N. Everybody got that? Do thumbs up if yes. Okay. Example 4. Our language is A to the I, B to the J, I strictly greater than J. Okay, guys, I am the demon. I'm hiding my horns under this hat. I want you to tell me the moves to make. Okay, so somebody tell me what should W be?
So,
Asa is
uh,
suggesting a to the p, b to the p minus 1. How do I close the chat? Excellent choice. Excellent choice. So Demon chooses y equals a to the k. Doesn't matter really what x is. And what do we know about this k? It's strictly greater than 0. It's less than or equal to p. It could be all the way up to p. So Asa, you chose that. So what is your choice now? Adam, can you tell me the choice?
he said I is equal to 0.
So you see, this is a really clever one because any positive choice for I would only push you up. So the only thing you can do is to try and push it down. And that's why she chose A and B so that they were right on the edge. Okay, so Asa chooses I equals 0. And the new string is A to the P minus K, B to the P minus 1, and K is strictly greater than 0. So P minus K is not strictly greater than P minus 1.
In the chat, Marianic just asked what would we have chosen if we had gone with Owen's answer, which was a to the p plus 1, b to the p.
Same thing. I mean, that's essentially the same choice. I mean, it could have been, you could have also chosen A to the 312p, B to the 312p minus 1. Okay, good. So this was an example showing that sometimes you got to pump down. What can we do now? Okay, so this is a slightly interesting example. It's actually super easy, but it's showing you a bit more variety than just A's and B's. So I'm hoping you will develop some kind of feeling for what's likely to be regular and what's not. At some point, you should have an instinctive feeling, oh, this can't be regular, or this is definitely regular. So here we go. My sigma is a slightly richer alphabet now. I'm allowed to use the binary numerals, otherwise known as bits. I'm allowed to use the plus symbol, and I'm allowed to use the equality symbol. And the language consists of strings of the following form: x plus y equals z, where x, y, and z are bit strings, and the equation is valid. So of course, this should not be a regular language because you're required to do some arithmetic to test. But let's just do it. So Demon picks P. I pick the following string: 1, 1, 1, P of them plus 0 equals 1, 1. Certainly a valid equation. So Demon is forced to pick y equals 1, some k of them, where k is strictly greater than 0 and less than or equal to p. So I pick any I not equal to 1 to win. Okay, so if you say, I have a language which consists of all binary additive statements about binary numbers, no way can that be regular. But that should not be a shock. What else do I want to do? Okay, let's try this one. Are we up to example 6?
Yes.
Good. So the language is a to the I, b to the j, GCD of I and j is 1. Certainly not regular, right? How am I going to test relative primality? I can't even test primality. Okay. This is, again, by the way, surprisingly hard to do. Just try it. I mean, it's possible. Of course, it's possible, but it's not at all easy. But we are going to convert it into an easy problem. So I will show L complement is not regular. So that certainly means L is not regular, because if L had been regular, L complement would also be regular. Okay, so let's look at L complement. So this means, so what's L complement look like? A big mess. So we're going to look at, just to be precise, L complement intersection A star B star. Okay. So in my notes, I didn't say that, but that's certainly what I intended. So Demon chooses P. So then I choose, since we use the letter P in the pumping lemma, we can't say P for generic prime number. So I choose Q strictly greater than P plus 1 with Q prime and W equals A to the Q A to the Q B to the Q. So of course, the GCD of Q and Q is Q, not 1. So it's in L bar, L will complement intersection A star, B star. All right. So now I have to pump it in such a way that it becomes relatively prime. Well, how do I do that? So Demon is forced to choose Y equals A to the K, with K strictly positive and less than or equal to P. So I choose I equals 0, another pumping down situation. So now we have xz, because we've just eliminated the y by setting I to 0, equals A to the Q minus K, B to the Q. So note Q minus K is greater than P plus 1 minus K. Why? Because we chose Q to be greater than P plus 1. And so this has to be of length greater than 0. Okay, so I know that Q minus K is actually strictly positive. In fact, it's strictly greater than 1. So GCD of Q minus K Q indeed equals 1 because Q is a prime. Hence, XZ is not in L complement intersection A star B star. So L is not regular. Okay, I think last example. So this is 7. So now my language L is, I'll just use the symbol 1 instead of A. So this is maybe slightly confusing notation because the first exponentiation is string notation, just saying I'm repeating this letter that many times. But the second exponentiation is a real exponential. So 1 to the 2 to the n. Okay, so what's in L? You can have 1, you can have 1, 1, you can have 1, 1, 1, 1, and I think I should stop writing. So powers of 2. Sequences of A of length, powers of 2. Okay, demon picks P. All right, what do you guys pick?
The chat seems a little bit conflicted. One person is saying the maximum out of P. Never mind, that person withdrew their answer. So the chat says 1 to the 2 to the P.
Okay. All right, my turn. So demon picks X, Y, Z such that length of XY is strictly less than P. Length of Y is positive, and XYZ equals 1 to the 2 to the P. So Y equals 1 to the K, where K is less than or equal to P greater than 0, and P, by the way, of course, is strictly less than 2 to the P. So this summarizes all the demon choices. What does the chat pick?
The chat is suggesting 1.
1. So 1 is the thing guaranteed never to work. I equals 1. So
Yeah,
if you pick I equals 1, it's exactly the same string. So how can it be out of the language?
the chat thinks it might be 2 now.
The chat thinks it might be 2 now. All right, then let's try this. Okay, so let's do some analysis. X to the Y to the 2z is equal to 1 to the 2 to the p plus an extra k. Okay, so let's do some analysis of this. So first of all, we note that 2 to the p is strictly less than 2 to the p plus k. Note strictly less than, because k is of course strictly positive. And of course, this is less than 2 to the p plus p, less than or equal to, because k may be all the way up to p, but definitely not more than that. Yeah, we do know one very important fact. 2 to the p is strictly less than, p is strictly less than 2 to the p. So this 2 to the p just corresponds to that one, but this p I've replaced with 2 to the p. And this, by the miracle of arithmetic, is 2 to the p plus 1. So you see 2 to the p plus k, you notice strict inequalities on both sides. It's strictly between two consecutive powers of 2. Hence, it cannot be a power of 2. Okay, so L is not regular. So I want to do a small follow-up puzzle. Given any subset of the natural numbers, we define two sets. One is called unary S. So unary S is a set of numbers like this, strings like this, I mean. S may be finite or infinite. If it's finite, it's certainly regular. And we'll define binary S. So unary S is simply all the numbers in the set S represented in unary notation, i.e. just by that length sequence of ones. Binary S is the same thing, except we were using binary notation. So it's a set of words in 0, 1 star such that W read as a binary number is in S. Okay, so everybody understands these two sets, unary S and binary S. These are parametric things. You give me an S and it determines these two sets of strings. Okay, so here's the question. If binary S is regular, does unary S have to be regular? Any thoughts?
The chat is saying no. The example given was 1 0 star is regular, but 1 to the 2 to the n is not.
Exactly. Oops. The answer is no. So if S equals powers of 2, then binary S equals 1 0 star, but unary S we just showed is not regular. What about the other way? So I will let you think about that because I don't remember the answer. So I will take a break now. Maybe we'll restart at 12:20. Let me do pause. Zoom recording. Thanks, Maria. So she also reminded me to mention the final exam format. So I am not allowed, after all, to have oral exams because they're, I don't know, they're afraid I'll terrify you too much or something. So we will have a take-home final. And I'm not going to get stressed out about who is looking up things on the web or not, because I have better things to do with my life than worry about things like that. Okay, so I'd like to talk, well, sorry, I have to go to speaker view. Yes, and then I have to do screen sharing. Share. Okay, connect, screen mirroring, Zoom Kanpur. Hello. Yeah, good. Right. So Adam, are you still co-host?
Yes, I am.
You're okay with that?
Yes.
It's not too much of a distraction?
No.
Good. So we wrap up the topics that I didn't make on Tuesday, and that's Kleene algebras. Trying to remember who invented Kleene algebras, but I can't. Wasn't Kleene. So do all of you know what the word ring means? Everybody knows what a ring is? No?
Many people appear not to know.
Many people appear not to know. In that case, I'll define something called a semi-ring. So in mathematics, rings are very, very important. In computer science, semi-rings are very, very important. And many algorithms that you learn in graphs and so on can be generalized to arbitrary semi-rings. So let me tell you what a semi-ring is. A set with two operations. So we call the set S, so the carrier of the semi-ring. So, and then the two operations are typically written plus, so it's a binary operation, and times, which is also a binary operation. And two constants called zero, that's an element of the semi-ring, and one written as one. Don't confuse these with the numbers 0 and 1. This is an abstract set with these two binary operations and these two distinguished elements. So S plus 0 forms a commutative monoid. S times 1 forms a monoid, which may or may not be commutative. So a nice example of a semi-ring. So sorry, and then there are many more axioms. So times distributes over plus. And is there anything? Oh yes, 0 annihilates with times. So what that means is that a times 0 equals 0 times a times 0, 0 times a equals 0. Okay, so that's it. That's a semi-ring. If S plus 0 forms a group, then we have a ring. So with that plus, it's always commutative. I'm just wondering if I'm missing any axioms. So a very important example of semi-rings are, so simple example, natural numbers with the usual 0 and 1 and with the usual plus and times. This is a semi-ring, not a ring, because I don't have inverses for addition, because I don't have the negative integers. If I take the integers, then I get a bona fide ring. There are other cool rings floating around. So for example, if I take this set, which is the set of all numbers of this form, then this is called the ring of Gaussian integers. And it's a lovely little ring, but let's not get distracted by it just now. So another example is matrices. So let's say n by n matrices over n. So these are things like this, where the A, B, C, D are all natural numbers. And then you multiply by matrix multiplication. And add component-wise. So a bit more algebra. An idempotent semiring. Let's say J is a semiring such that for all x in the semiring, x squared equals x. So here's the example I have in mind are true and false. With this as my plus operation and this as my times operation. If I have any semiring, the set of n by n matrices form a semiring. So that's actually where this subject gets its power from. So bits, true, false, that's like a very, very simple algebra, not much is going on. But Boolean matrices form a nice semiring. And they are, in fact, an idempotent semiring. And so with Boolean matrices, you can do lots of things. Yeah. Okay, good. So this is kind of a warm-up for Kleene algebras. So a Kleene algebra K has a set of elements It has two binary operations, typically written plus and times, but this time I'll write times just as a dot. It has two constants, 0 and 1, and it has another special operation which isn't there normally in rings, and that is star. And you should think of this as I'm about to axiomatize the Kleene star operation. So what are the axioms? S plus 0 forms a commutative monoid. S times, brain is running ahead. S times 1 is a monoid. So basically, S plus dot 0, 1 forms an idempotent semiring. And now I have to tell you what are the equations satisfied by star. And now some star equations. So the first one is going to say 1 plus a star equals a star. The second one is going to say 1 plus a star a equals a star. Okay? Mysterious looking equations, but perhaps you recognize them. And now we are going to introduce, it jumped out of my hands. Okay, we introduce a partial order. By saying A is less than B is defined to mean that A plus B equals B. So you need to check that this is really a partial order. But it is easy. Okay. Having introduced this partial order, I get to tell you the last two rules. So these are rules, not equations. So this rule says that if B plus AC is less than C, then A star B is less than C. And if B plus CA is less than C, then BA star is less than C. So I have to state all these rules twice. It's basically each pair is really more or less the same rule. It's just that the damn thing is not commutative. So I have to write both versions with each one on either side. Okay, so that's it. That's the definition of a Kleene algebra. It has all these equations. It induces a partial order, and you can verify from the equations given that this really is a partial order. And finally, we have these two rules based in terms of that partial order. Okay, so let's give examples of Kleene algebras? Adam, anything exciting happening on the chat?
Um, they're asking whether it's idempotent with respect to plus or with respect to dot.
Oh, yes, good. That was an important point. Idempotent semi-ring. So it's with respect to plus. So A plus A equals A. Very good question. Very, very good question. Anyway, good. Examples. First example. um, let sigma be a finite alphabet. And let S equals regular languages contained in sigma star. Okay, with plus interpreted as union and dot interpreted as concatenation. So if you remember, concatenation of languages means you take every word from the first language and every word from the second language, concatenate them, so you get a whole bunch of new words. That's the concatenated language. Okay, always two pieces, one from this language, one from that language. Any combination, you put them together. And of course, this abstract star of the Kleene algebra is the Kleene star. Okay, that's our canonical example and the thing that inspired us to call these things Kleene algebras. So that's the first one. But other fascinating things happen. If we take S, any set, and R to be the collection of binary relations on S. So remember, a binary relation is just a subset of S cross S. It's just a subset of S cross S. It's a set of pairs, and it doesn't have to satisfy any axioms. If it satisfies certain properties, then we give it special names. So for example, if it's reflexive, transitive, symmetric, we call it an equivalence relation. If it's reflexive, anti-symmetric, transitive, we call it a partial order. If it's just reflexive and transitive, we call it a pre-order. And if it's any old thing, we just call it a binary relation. So binary relation by itself has no specified properties, not even reflexivity. Okay? So how do binary relations form a Kleene algebra? So plus is union. And what do you mean union? Well, I just said a relation is a set of pairs. So you take two relations, you just throw all the pairs together. And that's just a binary relation. There's no conditions on being a binary relation. It doesn't have to be transitive or anything. So this operation is always defined. This operation is relational composition. And what does that mean? So remember, we use notation like this, X, R, Y, to mean the pair XY belongs to the relation R. That's considered kind of dorky to write it like that. So we tend to write it like this and read it as X is related to Y. So relational composition says, I have a new relation, let's say R dot S, and we'll say that X is related to Y by R dot S is the same as saying there exists a Z such that X is related to Z by R and Z is related to Y by S. So this is relational composition. Okay, and 0 is the empty relation. Nothing is related to anything. That's also a binary relation. And 1 is the identity relation. So it's a set of all pairs like this. So it says every element is related to itself and to nothing else. So you can check all the axioms of a Kleene algebra. But you can ask, what the heck does star mean for relations? So R star is the reflexive, transitive closure of R. And what does that mean? So what you do is you say X is R star related to Y if there exists some N and Z1 through Zn such that X are Z1 and Z1 are Z2 and Zn minus 1 are Zn and Zn are Y. Basically, the transitive closure of a relation is you take two elements, and if you can find a chain linking them with a sequence of R steps, then you relate X and Y. Okay, so this is the transitive closure. So whatever R you start with, R star is guaranteed to be transitive because you explicitly constructed it to be like that. If you're thinking in terms of graphs, graphs are a nice way of picturing relations because you can take the elements of the set to be the nodes and you draw an edge precisely if there is an arc from X, draw an edge from X to Y precisely if X is related to Y. So this is always a directed graph. If the relation is always is symmetric, then of course it becomes an undirected graph, but a general binary relation will be a directed graph. And then the reflexive transitive, the transitive closure is you take the paths in the graph. Okay, so that gives you perhaps a more visual picture of what the transitive closure is. Reflexive transitive closure, I said, so you also automatically throw in everything is related to itself if it was not already related in R. Well, you add that also. Okay, so this operation is called the reflexive transitive closure of a binary relation, and relations with these operations and those constants indeed form a Kleene algebra. So everything we proved about regular expressions automatically applies to relations. Well, not everything, because there's no such thing as concatenation. You have to interpret it the right way. Okay. Now I want to show you two more examples in a minute, but first I just want to state a theorem that I'm not going to prove, but it is actually very easy. So supposing we have an equation. Okay, so we'll have ax plus b. So a and b belong to my Kleene algebra, and x is a variable. And now I'm telling you, solve for x. That's not an equation, is it? It's ax plus b equals x. There we go. Solve for x. And it turns out you can check. You can check either in the general context of Kleene algebras or in the specific context of regular expressions. A star b is the smallest solution. So what do you mean by smallest solution? Well, first of all, it's a solution. Let's see if you can check that. A star, B plus B. So this is equal to A star plus 1, B. But didn't one of our equations say that 1 plus A star is just A star? So this is equal to A star B. Okay, so this shows that it's a solution of the equation. So this is just from the rules of Kleene algebra and helps applies to relations, applies to regular expressions. So this is actually great because it tells you, hey, you want to solve equations for regular expressions, you have a rule that tells you how to solve linear equations. So now, what does it mean to say it's the smallest? If capital X is another solution, then A star B is actually less than X. So it's not that there's a unique solution, but there is a least solution. So there's a special one. So solving equations like that is not super interesting. It's a kind of a curiosity, but the next thing I'm going to do is makes it extremely powerful. What's happening on the chat?
What we're talking about is does taking the union with an empty set act as an identity, and
Yes.
before, okay. And before that, somebody was just asking for a clarification of which identity is which.
Right. So 0 is the identity for plus, 1 is the identity for times, as you're used to from arithmetic. Yeah, so what is 1? I didn't tell you what is 1 in the interpretation of Kleene algebras as regular expressions. So it's the language containing only epsilon. Okay, so example. So in fact, this is a meta example. If K is any Kleene algebra, define M sub nk to be n by n matrices with entries in K. And the crucial point is this can also be organized into a Kleene algebra. So let's look at 2 by 2 matrices. Just to illustrate, but it works equally well for n by n. So when you want to add these things, of course, you just add them component-wise, and so on. The more interesting operation is matrix multiplication. You just use, so you see the matrix multiplication rule, which we were always taught, this has to be times, and then you take the rows and the columns and you add up the corresponding, multiply the corresponding things and add them up. Well, as soon as you have two operations, you can do that. It doesn't have to be the times and the addition of arithmetic. Anytime you have two operations and they have the right distributivity laws, bang, you've got a matrix concept going. So Boolean matrices can be multiplied, whereas of course, instead of taking plus and times, you take or and and. So similarly, matrices of elements from a Kleene algebra, you do matrix multiplication using the plus and times of the Kleene algebra. So it's A prime plus B, C prime. And this dot is the Kleene algebra dot. This plus is the Kleene algebra plus, and all the other entries are just as you might expect from what you know already about multiplying matrices. Now we come to the cool part, which is what the hell is star? So of course, what is zero? Well, you put zeros in every element of the matrix. But what's one? It's the usual ones along the diagonal and zeros everywhere else. That's the usual identity for matrix multiplication. That works in this case also. But what is star? So star is like this. I'm sorry, sometimes I've written these with big parentheses and now I'm writing them with square brackets. It's all the same. It's just a matrix. So the star of this guy is given by the following magic formula. And instead of giving you a justification that all this thing, I'm just going to draw a picture that might explain to you why that's the right formula. So this is A plus B D star C star. And over here you have A plus B D star C star B D star. Over here you have D plus C A star B star C A star D plus C A star, sorry, C D plus C A star B, that whole thing star. Now this seems like we cooked this up by black magic. So you can actually verify with a lot of painful calculations that I'm not in the mood to do, that all the relevant axioms for Kleene algebras are satisfied. But the way Dexter Cozen likes to explain this is he says, if you stare at the following, what he calls mandala. Does anybody there know Sanskrit? Mandala is a Sanskrit word, but I've forgotten what exactly it means, some kind of mystical figure. So here we go. Here's our mandala. 2 dots. So what's the matrix? What's the Kleene algebra doing? It's telling you how to get from one place to the other. Okay, now if you look at this picture, you can say, how do I go from A to A following these loops? Well, I can do this, then I can go there, then I can go there a number of times, and I can come back, and I can just repeat that as many times as I want. And I'll end up from A to A, and that's indeed the first entry. You ask, where did the second entry come from? Well, you ask, how do I get from A to B in this picture? Well, I can go like this, then I can go like that, and I can
Um,
repeat that as many times as I like. Then I can go there, and then I can loop around as many times as I want.
Professor, if you're like drawing something or tracing it out with your mouse, the screen hasn't updated in a while.
Really?
Uh,
So on my laptop, it shows, you don't see this picture with the two dots?
um,
No, I think it's fine. I mean, it is 1 p.m. on the iPad, which is the actual time.
no, I meant there was sort of a stray mark in the bottom right, and I didn't know if that was like you getting halfway through something and then it not sharing properly.
Okay, so but you're seeing this picture with the loops
Yes.
and the BC. Okay, so from this picture you derive, of course, you still have to prove by equational hacking that it satisfies all the equations of a Kleene algebra. But this is basically how you cook up or conceptualize the correct formula for the Kleene star of a matrix. And now, whoa, sorry, that was erased. Now we can solve matrix vector equations. So our old formula that says I can solve an equation of the form little x equals ax can plus b can be rewritten as, so this is a matrix and these are vectors. And you can use this thing to actually solve. So this can be used to construct the regular expression associated with the DFA. So Dexter Cozen didn't invent Kleene algebras, but he has developed the theory tremendously and extended the theory. Tremendously, including probabilistic extensions. And all kinds of cool things have been done, like designing a programming language for network programming based on Kleene algebras. So he has introduced a thing called Kleene algebra with tests, which is not just Kleene algebras, but you can also do Boolean valued tests of certain properties. So in addition to the Kleene algebra, there's another Boolean algebra that's interacting with it in the right way. And then he's introduced probabilistic Kleene algebra with tests. Okay, so I'm going to stop there. And I do have to get off and get going. Let me just say a few remarks about the homework. So we will expect you to upload it on my courses sometime on Monday. We will post the solutions, I guess, Tuesday morning. And we will ask you to look at the solutions and assign yourself marks, but we will also look at the things you've turned in and see if they match. Okay, very good. I'm afraid I have to leave today, so I don't have time for a long chat, but I will see you all on Monday. Have a great weekend. Does anybody know the add drop date for this class?
I think that for summer courses, it is today, the 4th lecture.
Aha, okay, so just to make sure you have the updated information, the final exam will be a take home. Probably I'll give you 48 hours or something to do it, or the weekend. And the final exam will mark everything, unlike the homework where we are sampling marking. Also, don't get bent out of shape over the homework. You know, some of the questions are very difficult. Some of them are relatively straightforward. It is not my intention to torture you into, you know, spending all your time trying to produce a perfect assignment. It's meant to stimulate you to think about it. That's all. The whole relationship is not one of, I have these precious things in my bag called marks that I give out grudgingly. The homework is there for you to, for your minds to be stimulated. Okay, bye. Have a good weekend.
Bye.
Bye.
Bye, Prakash.
Bye.
Bye.
Goodbye.
Prakash,
Bye.
weekend.
Thank you.
Thank you.
Okay, end meeting.